Now, moving on to some interesting applications of our understanding in the atmosphere. In the upper atmosphere is the stratosphere, and this is where the ozone layer is located in the lower half of the stratosphere. And the concentration of ozone there is in the single to low double-digit part per million level, so 10, 15 parts per million ozone. And in that location, the atmosphere, ozone is created and destroyed continuously through interaction with ultraviolet light coming from the sun. And it's this chemistry that's going on that removes much of the UV radiation that otherwise would strike the planet's surface. And this is converted to heat. So light from the sun will cleave ozone to give us molecular oxygen and an oxygen-free radical and generate heat. This is an entropically favored reaction. The heat of formation is a net zero because it's in equilibrium. The number of moles of gas are increasing, so this is an increase in entropy. So this is how it is a spontaneous reaction. Now, I mentioned ozone, the beneficial aspect of ozone in the stratosphere. If you watch the weather reports, you've likely seen warnings about ground level ozone. So when ozone is in the troposphere, the lowest level of our atmosphere, ozone can form through there are natural sources of ozone, ground level ozone, but there are anthropogenic sources of ozone, man-made ozone. And when ozone is in the few part per billion levels, now we're talking about 1,000 times lower than in the upper atmosphere. So ppm level in the stratosphere, ppb level in the troposphere. At that 5 to 10 ppb level, long-term exposure can lead to lung damage. So there may be warnings for people with respiratory illnesses to stay indoors on ozone alert days. The level of ozone in the troposphere, in this part per billion level, is not sufficient to be a significant heating source for the atmosphere. At 1,000 times higher concentration is where we see that effect in the stratosphere. So I think in the textbook, the discussion of chlorofluorocarbons is there. In the 1920s. Scientists working for General Motors developed a class of compounds collectively known as freons, chlorofluorocarbons, to use as refrigerants. And their use increased. Before that, ammonia was a common refrigerant. Before freon, air conditioning installations tended only to be in large buildings. So, this would have been in the 1920s. It was common for movie theaters to be air conditioned with ammonia-based refrigerants. And they had a tendency to catch fire and explode. So movie theaters, the phrase of you can't yell fire in a crowded theater has some added weight behind it, because fires in theaters were a particular hazard in the early part of the 20th century. So I'm not going to get into the nomenclature of freons. There is a nomenclature scheme that was developed. Midgley and Heen developed in 1929 a naming system for halocarbons, and then that was refined a few years later by a person named Park. you can look this up if you're going to be working as a chemical engineer. It's likely that you'll encounter the Freon nomenclature system. As a chemist, you'll encounter it when you try to purchase these materials, but it's not going to be part of our class. In 1974, a professor from UC Irvine and his postdoc, it was Sherwood Rowland, and the postdoc was Mario Molina. They shared the 1995 Nobel Prize with a German scientist, Paul Crutzen, for the research that showed that chlorofluorocarbons led to the depletion of ozone in the upper atmosphere. So this is a serious health issue, because without ozone, the planet receives much more harmful UV radiation. So we would see many more skin cancers and degradation of materials from that high energy radiation. The compounds are relatively inert, so they reach the upper atmosphere, and it's there that they interact with UV light to form chlorine radicals. The chlorine radicals then destroy the ozone, and the mechanism is shown here. Bond cleavage to generate a chlorine radical and the Freon radical. The chlorine radical then goes on to react with ozone, producing O2 and a radical in this propagation step. And then this radical species reacts with an oxygen radical to produce a second mole of O2, producing 2 moles of oxygen. So the, let's see, I guess it was the Vienna Convention. I was going to say Kyoto Protocols, but they came much later. The Vienna Convention was a agreement among most of the nation's economies to replace chlorofluorocarbons with hydrofluoroalkenes. So these will sometimes be referred to as HFCs, and they also have a nomenclature system. This may be the same as for the freons. It's more than I want to go into. They're not harmful in terms of consuming ozone, but they are greenhouse gases. So in the Kyoto Protocols, there were further commitments to reduce the use of HFCs and to continue to look for alternatives. At the time that this went into effect, I was working in the pharmaceutical industry, and metered dose inhalers, asthma drugs typically, many of those inhalers, most of them, were formulated with freon propellants. And there was a significant need to reformulate the products using the HFCs, and not all the products could be redeveloped as metered dose inhalers, and the dry powder inhalers that are now quite common were developed in an effort to move away from the propellant-based inhalers.